Okay, so I will just be making a short summary of what we will be discussing this week, basically the Green theorem and the method of images, and then we will pass to your questions. Now, and we had already discussed the Green theorem. It basically allowed us to write down the solution for the potential. We are looking for the potential in a given volume. Let's say we have our volume. This is our volume V, and then we have the boundary of the volume V. Inside this volume, we have certain charge distribution, rho of r prime. And we said that by using Green theorem, we could write this in the form of a volume integral, rho of r prime, multiplied by some function, which we call the Green's function, plus some integral over the boundary of the volume V of, well, we had basically two different kinds of terms. Either we know the potential at the boundary, or we know the value of the derivative of the potential at the boundary. And this was our final result. I might be missing some 1/4 pi's over here, but I mean, they don't really affect the discussion, the general principle. Now, we also know that we could write the potential, any potential in fact, if we know the charge distribution everywhere. This is nothing but dV prime, let's say, let me call this rho tilde, r prime divided by r minus r prime. This is the potential everywhere. So basically what this Green theorem, the potential obtained by using the Green theorem and the potential obtained by the integral over the whole volume, well, they should match. We are talking about the same potential. But the difference between these two approaches is that the second, the integral over the all of space, not only our volume, assumes that we know the potential everywhere in space. So we can, in principle, separate that volume integral over all space into a volume integral over our volume plus a volume integral over all space except in our volume. So we can separate that integral, and then the potential, we should be able to write the potential in the form dV prime rho tilde r prime over our volume plus another integral. Here we have the r minus r prime dV prime rho tilde of r prime over r minus r prime over all space minus our volume. But you see, rho tilde is the charge distribution everywhere in space. So it has the information about all the charges in every point in the universe. Whereas rho is the charge distribution only in the volume that we are interested in. But that information is kind of already in rho tilde. So basically, rho of r prime should be equal to rho tilde of r prime if r prime is in our volume. So in our volume, they should match. I mean, we are talking about the same charge distribution. So in that case, the first integral is just rho of r prime divided by r minus r prime plus dV prime rho tilde of r prime divided by r minus r prime. Now the Green's function that we talked about, that we wrote here, is actually nothing but 1 over r minus r prime. This is nothing but the potential of a point charge, a unit point charge, plus some other function which satisfies the Laplace's equation, no charge. So if you compare this solution And the solution we have using the Green's theorem now, if you compare the two, well, you see this term is already included over here because G contains this 1 over R minus R prime. And plus there are some additional term, which is this F in our the result of the Green's theorem. That F plus the surface integral should be equal to this volume integral over here. That volume integral over all space except an R volume. Well, that all space except an R volume also contains the surface. The first integral is inside the volume, and whatever is not inside the volume is in the other part. So basically that surface integral over here and this function f over here kind of mimics the effect of all the charges that are not in my volume. And then, okay, once we have the Green's theorem, we had two of them, we could use the Green's theorem to prove that the solution was unique. So if by some means we find the solution that satisfies our boundary conditions on the boundary of our volume, and that it gives the same Poisson equation inside our volume, if we find one solution, then the uniqueness just tells us that it is the only solution. So we don't need to worry about the possibility of other solutions or missing some solution. So that is the kind of the power of the uniqueness theorem. And then we kind of employed this uniqueness theorem in deriving some the potentials created by point charges in certain volumes. Like you had studied the example of infinite conducting plane, grounded conducting plane, grounded sphere conducting sphere, or there's even an example where the sphere is not at the same potential, but both hemispheres are at different potentials. Although they look kind of, most of the time you will be dealing with boundary conditions that are zero. But you see, that is one thing that Green's theorem also tells us. You see, if we know that our function is zero at the boundary, or let's say, if we know the value of our function at the boundary, and we have an arbitrary charge distribution, if we want to find that, it's enough to find the G in this Green's theorem such that the G is zero on the boundary. And it satisfies del squared phi is equal to minus del squared G minus 4 pi Dirac delta R minus R prime. We should find the G that satisfies this Poisson's equation, which is the boundary, the potential created. It's exactly the same as the potential created by a unit point charge, subject to the boundary condition that G on the boundary of B is equal to 0. Because if we find such a G, then assuming that, of course, we know the value of our potential at the boundary, it can be as complicated as you want. And in the example, it was just two hemispheres at different potentials, but it can be as complicated as you want. There are no limitations over there. To solve that problem, it's enough to solve this problem. Because if you solve this problem, well, the G at the boundary is 0, so this term is 0. Then you need to evaluate the derivative of G with respect to the normal direction on your surface. And you need to know the values of phi at the boundary, which we assume that you are given. They might be complicated, but you are given. So everything you know. There's nothing you are missing in this integral. So if you can evaluate this integral, or if you just have some computer code that can evaluate this integral, you know the solution of that complicated charge distribution with complicated boundary conditions by just solving the point charging with 0 boundary conditions. So that's why we will be dealing with point charges with zero boundary condition most of the time. For example, in one of the questions, there is a sphere question where you have an image, it's not grounded. So what you do is, it can be fixed at a given potential. So if it was grounded, then we know that there, for one charge, there's one image charge, and the potential on the sphere is zero. Well, if it is not grounded, then it should be neutral all the time. If you start with a neutral sphere, it should stay neutral. You put one charge, then there is the image charge. Well, the surface of the boundary should be the same potential. To create us the same potential and also conserve the charge, you put the rest of the charge at the center of the sphere. So that creates a constant potential on the surface of your conductor. That is one way of solving it. But you could have just used the solution that for zero grounded sphere, that is the Green's function G, put it over here for the non-grounded sphere. Well, you know the charge distribution rho of R prime. You have already evaluated G. You know the new potential is constant phi. You know the value of phi on the boundary. And you could have also used exactly this equation to obtain the solution for non-grounded sphere if you could determine the potential for a grounded sphere. Now, that's not done in the book, so that will be your next homework. So that's the basic idea of this, this chapter. So we have this infinite conducting plane. We have this point charge out of the conducting sphere, grounded conducting sphere, non-grounded conducting sphere, non-uniform potential on the conducting sphere, and then there was a conducting sphere in a uniform electric field. So because if you put it in an electric field, we know that it will be, the charges will move in the conductor, and hence they will modify the applied electric field, and hence the potential. Those were the examples in this chapter, if I'm not missing any other example. Now, later on, we will study these problems again, by the way, by other means. So this is just, I mean, if you have, again, symmetrical objects, we will be dealing with infinite planes or spheres, etc. So they are also quite symmetrical. Now, we will be using other methods which can be applied for systems that are not so symmetrical, like the method of images, and we will apply them also in to these problems to see how they work. Now, your questions.
The example with two plates at an angle.
Okay. So this one. You have these two semi-infinite plates. They make an angle theta, and theta could be pi over 4, pi over 2, what else? Pi over 3.
My question is about the charge density at the surface. The book finds it from assuming that there is no electric field outside these plates.
Mm-hmm.
How do we justify this assumption?
Well, let's say we are grounding it, right?
No, we have the potential grid. We have potential.
Okay, so it's like there's a constant potential of these plates. Well, there are a couple of things you can say. You can say, okay, these are infinite plates, but this is also conductor over here. So that is kind of, well, it has to be zero, the electric field inside the conductor. Well, this is our empty region. Empty over there, or conductor on the other side of the place. That is one possibility. Or you could have also said this one. Let's study the potential in this volume. It goes to infinity. Okay. So what is the Poisson's equation in my volume? What is the charge distribution inside my volume? 0. Phi on the boundary of my volume. Is equal to V. So let's try this one. Does it satisfy the post-Laplace equation? Phi is just constant V. It satisfies the Laplace equation. Does it satisfy the boundary condition? Well, so this is the solution because of the uniqueness. So the potential in that volume is constant. So constant potential means zero electric field. If we had, for example, one of the plates at the potential V, the other plate at some different potential, then this won't satisfy the boundary conditions. So we would obtain some electric field in that region. Which zero radius?
Between the two plates, talking about points very close to the origin, very close to the point where they intersect.
Yeah, okay. So you put a charge, you put some charge over here, right? No, nothing. No, you should put some charge somewhere. Yes, others? No, I shouldn't be replying, you should be trying it first. Let's take our shape, U shape. So what is the example exactly? Do we have some charge inside these plates?
If you have charge, the book applies automatically to the inside of the two plates. If we had charge,
Okay.
it wouldn't satisfy the last equation. I mean, we would have Poisson equation.
Sure. But this is a method of images problem, right?
Okay, we solved it normally by differential equation, by separation of variables.
No, we are not yet doing separation of variables, though. I mean, we are only doing the method of images. So we will be studying the method of separation of variables later on. But even with the separation of variables, what's the problem?
Point charge Q is located in between two grounded conducting planes.
A bit louder.
A point charge Q is located in between two grounded conducting planes which intersect at the angles.
Okay, the second part.
Second part. Second one. Furthermore, calculate potential phi. Am I right?
Reza, just come a bit forward.
Calculate the potential phi, the components of the electric fields, ER and E phi, as well as the surface charge density sigma in the neighborhood of rho equals 0.
So here, this is the question. This is the point of the book. Now, at first, we are talking about a problem with the point charge inside. But then we finished after the electric field. And then we assumed something different.
Well, is it?
So if you continue with the problem. So we assume that we have a potential now, although we were grounded. So which means we have a new problem now. And then we stated the Laplace equation instead of Poisson equation, which means that we don't have a point charge.
Hold on.
So that's why I assume that this is a new problem, which the author didn't mention that it's a new problem.
Well, let's see. The problem looks at, it's not really a new problem, but what it is saying is you have some charge over there. But then it asks you to look at the potential over here. In that region, there is no charge. So you calculate the potential with this point charge somewhere over there. And that solution satisfies not the Poisson equation, but the Laplace equation close to that corner. Because the charge is not close to that corner, not necessarily close to that corner.
But then the boundary condition should, like the boundary should exclude that charge.
Not necessarily. Now, you see, what we said was, for example, if you remember last week, we looked at this one. This is at the position, let's say, R0, and we are looking for the potential. We said that the Laplacian of phi is equal to 0 if R is not equal to R0, except at that point it satisfies the Laplacian. So we are basically doing the same thing over here. We have some charge somewhere.
When we try to solve
Mm-hmm.
what's the equation, we consider that.
Okay, no problem with that.
So we have two equations giving the same, applying the same distribution.
Now you see, in this region, they are the same equation because charge density is 0. Or at least, let's say, in this region.
What about the boundary?
Yeah, it's the same problem. The boundary is,
Same boundary.
I mean, they have a common boundary over here. Okay, you should ask your friends. I'm constantly answering your questions. Look at them, not me.
Shouldn't the boundary be different then? Because we can't send the other boundary to infinity. Because we have a charge there. If we send the other boundary to infinity, we have to include that charge. Right. If we assume that there is a boundary, we need to find the value of that boundary and then solve the differential equation from the potential.
No one? No comments? So let's start with, did you understand the question? Yes or no? Okay, if you didn't understand the question, he's over there. Ask him. What didn't you understand about the question?
Should I repeat it?
Hmm?
Should I repeat it?
I don't know. They don't say anything. So, no. Repeat what? What didn't you understand about the question?
The small volume.
Hmm?
On small volume.
So my question is, can we consider a soft volume with the same boundary? That's my question. But if you consider the same boundary, just these two plates, like with a smaller volume, not an infinite volume, then we have a path where the boundary is not given by the path. So can we consider this alternative problem? Is it valid?
Now did you understand the problem? Because now I will pick somebody to explain me the problem. So if you didn't understand, you should better ask him again. Okay, so everybody understood the problem. Yes, Anil, what's the problem that he's asking about?
If the plates are like infinity, but if we have a sub-volume, so the result is changed because we have a boundary in that volume.
Is that your question? So what do you think?
Potentials are same in this boundary, so even if it's infinity or not, even if we have a boundary, if the potentials are the same, the solution will be the same.
But we don't know the boundary, right? We don't know the value of the at the boundary.
We know the value at two plates. We don't
Okay.
know the value at anything that closes the relation.
The plates are still covered.
Can somebody tell me the answer? What was the answer to this problem?
Which answer? The field or sigma?
We are talking about the potential.
Potential is V plus sum of A sum rho to the n times pi over beta.
Mn times.
N times n. Pi over beta times sine n pi. No, sine is not
Okay, it's not at the power.
sine n beta phi over beta.
M pi.
Phi over beta.
This one, so this is also M. What are AM? What are AM? There should be some logarithms, no? Or no? They're cancelled. Okay.
Around zero is close to
Okay. So we don't know what AMs are.
we don't know what the ends are.
So we don't know the potential.
Unfixed particle distribution is not zero.
So, well, you are right. We cannot determine the potential if we don't know the potential at the boundary, at all of the boundary. So in the question, they don't determine it. They don't know the potential at the boundary. We know that there are some charges somewhere, so it's non-trivial. It's not, phi is not just V. That is what we know. It's not just constant. But we don't know what it is because we need, as you said, we need some additional information. Okay.
Relying on the first solution, when we consider the point charge, if we draw the boundary, then we close the region.
Okay.
So then we can evaluate the AM.
If you know the boundary, yes.
We should know it.
Yeah, I mean,
Because of the previous.
yes, exactly. So, of course, then it depends on the boundary condition. Once you know a way to determine your boundary conditions on all the boundaries, I mean, the boundary of the volume, it should be a closed surface. It can be at infinity, but it should be a closed surface. And you have to know the value of your potential at everywhere on the surface, either the potential or the derivative of the potential. Only in that case you can determine phi uniquely. If not, you cannot determine phi uniquely. Does it study the cases where, for example, the beta is larger than pi?
All the examples are 90, 60, 45.
Okay. So, for example, an interesting problem would be what happens if phi is larger than pi? If you take the limit as phi goes to 2 pi, for example. So if phi goes to 2 pi, you have a pointed tip. Right? And I'm sure you have always heard that in front of at the pointed regions, the electric field becomes very large. So here is your answer. Of course, if you solve it for beta goes to pi. You don't need to know what the AMs are. The only thing you need to know is, well, you can express the electric field in terms of A and AMs. And so if their coefficient diverges close to rho is equal to 0, then you know that close to the pointed tips, the electric field diverges, whatever the values of AM are. As long as there's no reason for them to be 0, they won't be 0. So you have a divergent electric field at pointed tips. So in such a case also, in such a problem, if the only thing you are interested in is whether the electric field increases or decreases, well, you don't need to know the boundary condition. Whatever the boundary conditions will be, close to the pointed tip, the electric field will diverge. Or in a realistic situation, you won't have this ideal pointed tips. Nevertheless, the electric field, you would expect it to become very large. Because in physics, everything is kind of continuous. So if you change the boundary conditions slightly, your solution should also change very slightly. There shouldn't be a drastic change due to a very small change in your boundary condition. So already now you can somehow get an idea of how to show that the electric field in a close to a pointed tip diverges.
But then the divergence, just a few minutes ago, we showed that there will be no electric field external to these states.
Yes.
Now you're saying that the divergence.
You see, this is my region, right? So I take it larger and larger. This is pi over 2. I make it, when they are pi over 2, I make it larger and larger. This is out of my region. Here there are no electric field. Larger and larger. Here there is no electric field. But this is my region. In my region, I can have electric field.
The two cases are symmetrical.
Not really. You see, in between your plates, you have some point charge somewhere, or some charges somewhere. That creates some non-trivial potential. You don't know what that potential is, but we don't need to know. The only thing we know is phi is, you see, before when I said that the electric field diverges if the coefficient of AM goes to, if the coefficient of AM diverges in the expression of the electric field, assuming that there is no reason for AM to be 0. If there are no charges in your domain, and at the boundary your potential is some kind of a constant, then there is a reason for AM to be 0. So there's no electric field. Nothing diverges. But if you put some charges somewhere, I don't know what, where, or what, I don't really care. If you put some charges, then there's no reason for AM to be 0, because the potential will not be constant in my volume. Then AM will have some value, depending on my charge distribution, etc. And then, if AM is non-zero, the potential will diverge in my domain, close to the tip. For example, if beta is, let's say, larger than pi, then you have the m is equal to one term. Well, m is equal to one term has the rho dependence. Rho is equal rho to the power pi over beta. Beta is larger than pi, so the exponent of rho is smaller than 1. If you take the derivative with respect to rho, that will be the radial component of your electric field, then that term will have a rho to a negative power. Because pi over rho, you see, assume pi over beta is less than 1. And rho of pi over beta, you will need to take the rho derivative, which will be pi over beta multiplied by rho to the power pi over beta minus 1. But pi over beta minus 1 is less than 0. That's why it diverges. Well, this derivative, you see, if you take the divergence of phi, this is del phi by del rho in the rho hat direction plus all the other terms. So this term diverges. So that's why you get well, in the idealistic case, you get infinite electric field. In the realistic case, of course, it won't be infinite. I mean, no plate is just so pointed. You get a very large electric field. For example, this will happen when pi is equal to 3 pi over 2. Again, you have this region. This is the zero electric field region, and you have some charge distribution over here. So here you have your pointed tip. Yes, other questions? Yes, Reza, you didn't talk yet. Any questions about this chapter? This one, you mean?
No,
Not this one.
for point charge. Potential for the point charge.
Okay.
Mention something about
This is the potential for a point charge.
something about putting the surface to the infinity. We have two terms in the general statement of potential. One
You mean this expression over here? Okay.
How can we eliminate the second term?
The second one, completely. Yes, answers.
So we have here.
Somebody else, please. You talk too much already. First of all, did you understand the question?
We reach from that flow expression about one. How can we eliminate the second surface intake?
So, did you understand his question? So why does he want to eliminate the second term? Emil? Hmm? Now that would have been nice, but that doesn't mean it's possible. So why does he want to eliminate? Yes, Cihat, you have been also silent. Did you understand his question?
Yes.
Okay. So what's the question?
He wants to get rid of the second term.
Why? I mean, why should it be possible?
Like it is possible if delta G over delta N G is independent of N,
Hmm.
but
Hmm?
I don't know.
Ask him.
Can it be independent or independent? But I know we can determine G arbitrarily. We determine G according to our problem. It can be dependent.
It can be, it cannot be. Why should it be zero? And more importantly, why does he want it to be zero? So what is he trying to achieve?
What if we have team wire? So yes, it will go to
So you see, ds is the surface of our volume. A thin wire, you mean we are looking inside the wire or outside the wire? If we are looking outside the wire, I mean, there are two things. The surface should be around your volume. So you cannot look at the outside of only this thin wire, but in that case, your surface should be the surface of your thin wire plus infinity. So both of them are the surfaces of your volume. And okay, so what will happen if you have a thin wire? So will it answer his question?
If you charge the solution everywhere, then we can eliminate the second term.
How?
We can not using this formula, but
Well, you see, this expression is valid. It It is true. It has to be true. This expression is also valid. It also has to be true. Both of them are true, whatever the configurations are, whatever your configuration is. Given that if you know sufficient information about your system, both of them are true, whether you use them or not. I mean, like 2 plus 2 is always 4. I mean, if you don't use it, that doesn't mean it's not true. It's always true. These expressions are always true. Now, one thing that I don't understand in your question is, why do you want to get rid of the second term? What makes you think that you can get rid of the second term?
What's the point of adding this?
We are not adding it. I mean, even if you say that we are adding it to what? Who told you that the potential should be the first term only? So why do you think that the first term is enough to satisfy our equations?
If we equate these two.
Oh, so that is your question. So you are trying to ask, in this one we only have a volume integral, in this one we have a volume and a surface integral. Is that the question? Okay. Okay, first, the warning for others. If you don't understand the question, you cannot answer it. Warning for the asker. If you don't ask the question properly, nobody will be able to answer your question. Well, the same thing holds for your pre-reports. I mean, sometimes in your pre-reports, I didn't understand this example. Well, the examples are long. So which point didn't you understand? So you should be more specific in your questions. It might be clear in your mind, but keep in mind that somebody else is reading them. And you are not there as a guide or somebody to explain what you mean. Yes?
In the first expression, we have two arbitrary scalar fields, phi and g, and we don't know are they equal or not.
Well, we definitely know that they are different, except in special cases.
Yeah, that's why we can do the same thing.
Mm-hmm.
First expression. Otherwise, we will have to go to the first. Volume integral, they are different. Yeah.
You want to talk about these two volume integrals?
Yeah.
You said different. They are same actually. Understand? G of G is equal to oh yes, we have plus of.
In general, they are not equal.
I think that's it. Second.
So if we put g equal that to 1 over r minus 5, right?
So second integral matches.
Hmm?
Am I right?
Depends on charge distribution.
Yes.
Depends on the charge distribution. Outside our volume, there is no charge.
Yes. And for your first question, the second integral is all of space. But the first integral is inside our volume and our surface. For second integral, we assume that there are no charges outside of our volume. But in the first expression, we said that yeah, there can be some charge outside of our volume. Okay, that's clear. we are trying to do things on the expression. First, we are trying to send volume to infinity, send surface to infinity. So we have all of the space again. So the first term stays and second term vanishes. And the other end, we are solving it for the surfaces. From the end is right. Again, am I right? Does it have for it?
The second integral is over V, not over all space.
Which one? The second one? No, it is overall space.
Not on the first expression, on the second box.
This is what the book assumes.
It means that when we take the surface to infinity,
Mm-hmm.
we can consider in the first integral, in the first expression, we can consider that V is also going to infinity. So that's why we can go back to this expression.
So what happens to the second one if you take the v goes to infinity?
The same since O is 0.
Well, the second term doesn't depend on rho. No, you mean that's not the second box. The surface integral doesn't depend on rho.
When you, in order to find phi, you need the divergence of G to be what? To be directed.
Laplacian. Laplacian of G is the direct delta, not the divergence.
Yeah, so the plus energy to be directed. So I guess this implies that the directional derivative of G, I don't know, is also proportional to 1 over R. I'm not sure.
So,
So if that's the case, then we have, 1 over R squared. So if that's the case, we have 1 over R cubed in the one term, 1 over R cubed in the other term. So if we take the surface activity, the area of the surface, proportional to R squared over R cubed, 1 over R. As R increases, we divert, it goes to 0.
okay, who will summarize what he said? So nobody was listening to you.
No, we must try to understand what we don't understand.
Okay, then ask him.
Okay.
Not to repeat. What didn't you understand? Repeat everything is just, he will repeat everything and the same way he did, so you will not. Either you didn't listen to him. In that case, you can ask him to repeat itself because you didn't hear anything that he said. Or if you listen to him, you should ask specifically, what didn't you understand? Then he might be able to rephrase the question in a way that will make more sense to you.
Okay, I'm rephrasing my question. I didn't hear anything physical in your question. That's mathematics. Can you repeat it physically?
Okay. Okay. Use.
Use that G and phi includes 1 over R cubed. R squared over R cubed.
R squared is for the surface, and 1 over R cubed is for 5 times delta G, or G times delta phi. We have 1 over R cubed, 1 over R cubed.
Okay, then at the end, if it's at the infinity, then it turns to divergence.
1 over R squared over R cubed, 1 over R.
Over R.
Okay.
R is at infinity. That means
Zero.
zero.
Yeah.
Yes, so?
So the second integral, the third integral vanishes.
Yes. Okay.
So if you increase the volume, this is like for every volume you take. If you are allowed to increase the volume for the same volume, which means that there's no charge outside the volume. Okay. So you you are free to increase that volume. You are free to send the surface to infinity. When you do, the surface integral goes to zero. Or it's shown to you. But I relied on a very specific point. I said that the Laplacian of G has to be Dirac delta. It has to be in order to arrive to this expression. But I don't know if that implies that del G over del N is proportional to 1 over R. I'm not sure about that. In the examples it is.
What is G? Physically. What does G correspond to? G is not arbitrary. It satisfies a particular differential equation with particular boundary conditions. G. So what are the equations satisfied by G? And also G on the boundary, let's just take the Dirichlet boundary condition. This should be equal to 0. So physically, what does this correspond to?
Charge density.
Okay, what kind of charge density?
The volume. Not the boundary of the volume, but in the volume there's a some charge.
What is the charge density inside our volume? Well, you see, I'm looking for G, which satisfies this particular solution. What is rho in our case? What does it physically correspond to? I mean, you have been asking for physical interpretation. Now everybody is telling me some mathematical symbol names.
There is uniform charge distribution in our sphere.
Uniform. Where do you see the uniform charge distribution? Where do you see our sphere? I don't see a sphere here in these equations.
I think G is the summation of the charge inside and the hypothetical charge outside, the summation of the potential.
You see, forget about the summation. These are the differential equations we have. Okay? So they describe some kind of physics, a physical system, a physical problem. What is the physical problem that this differential equation describes? I'm not looking for the solutions yet. Is it a uniform charge distribution, for example? A point charge. This is just a point charge on our volume. And what specifies our volume? You see, on the volume, the potential is 0. So you can say that you can imagine, for example, a conducting surface, closed surface, which is grounded. This is what the second equation tells me. The potential is constant at the boundary, so I can just imagine it to be a conducting surface. Not necessarily, but given a conducting surface, it will have the second boundary condition. And inside this conducting surface, we put some point charge at the point r prime. And this is the potential. Now the question is, we are sending this surface to infinity. So actually there is no surface. But the potential at infinity is 0. So we are looking at the potential of a point charge. And the potential, we know that the potential is kind of arbitrary because we can always shift the potential by a constant. And that constant is fixed by the boundary condition at infinity, which is 0. So if delta V goes, our surface goes to infinity, then what is the value? What is G? We already know it. It is the potential of a unit charge, which is r minus r prime. This is the potential. So then, as your friend said, on the surface, Well, the surface is now going to infinity. R prime is some point over here. G goes like 1 over R. It has to. So its derivative should go as 1 over R squared. Now you see, G goes to 1 over R. Derivative of G goes to 0 as 1 over R squared. Now the other problem is, what about phi? Phi is kind of arbitrary. Phi is the potential created by our charge distribution. But remember, in this problem at least, we will be always assuming that the charge that is created with phi is kind of localized. I have some charge distribution over here. And we are looking at this potential at very far away, at almost infinity. So from infinity, whatever this charge distribution is, it will just look like a point. So since it will look like a point, the potential should also go as 1 over R. Well, close to our charge distribution, it can have a complex shape, but at very large separation, it will be 1 over R. You can also see it from here. Look at the first term. You see, R is very large. It's almost at infinity. R prime is something over here. R prime is small. Now you can choose your origin somewhere over here, so R prime is small compared to R. But G, if one of the arguments goes to infinity, just behave like 1 over this larger distance. This is because G is equal to 1 over R minus R prime. So this is just 1 over R when R is very large. Well, I can just take it out, so phi behaves like 1 over R. Plus, of course, the correction due to the boundaries. So phi also behaves like 1 over R. So you see, this G is 1 over R. Derivative is 1 over R squared. Phi behaves like 1 over R. D phi by dn behaves like 1 over R squared. So both of those terms behave like 1 over the distance squared if the surface is very, very far away from my charges. Well, the surface also grows, so it just becomes 0 times infinity, because we have an infinite surface integral multiplied by a function that is 0. So you have to take a suitable limit. The function goes to 0 as 1 over R cubed. The surface goes to infinity as R squared. If you multiply them, the product goes to 0 as 1 over R. So if you take the limit of your volume to infinity, in that case, only in that limit, this expression behaves the other expression in this other box. So you see, both of these expressions are exactly true in every case, but they are just telling me different things. So in this expression, in the first box, I have this rho. So what is rho? Charge distribution inside our volume. Now, the first expression doesn't really care if I have charges outside my volume. Now, I might have some charges, and in general, I will have some charges both on the surface and outside my volume to create the required boundary conditions. But that volume integral doesn't care about the other charges. I don't need to know them. But of course, the influence of other charges, somehow I have to take them into account. And those are taken into account by the surface integral plus this function f. So both this function and this surface integral takes into account all the other charges that are not in my volume. Whereas in this other expression, this rho is the charge distribution of all of space. Of course, if the only charges in my space are in my volume and my surface is at infinity, then both of these expressions should match, and they do. So in general, we cannot get rid of the second term. It is there. And that surface integral is necessary. I'm sorry, I don't have this vector sign over here. It is necessary to take care about the influence of the charges that are not in my volume. But this expression with the surface integral is exactly equal to this expression over here, where the integral is over all the charges, not only the ones inside my volume.
G is a representation of external pressure.
Not all of G, F is. You see, I have this F. This is the potential of a point charge only. And remember, in this problem, G is actually the potential of a point charge with zero boundary conditions. So if the boundary was at infinity, and I only have that point charge, then I would have this 1 over r minus r prime. That's the only thing I would have. But then I bring this boundary, put this boundary. Say that, okay, I have this point charge subject to these boundary conditions. Okay, and those boundary conditions in the evaluation of G, I will just set them to 0. Okay, so it is 0, fine. But then, how do I impose this boundary condition? Well, basically, you just put some conductor on your boundary and ground the conductor. So that will make sure that on the boundary, the potential is 0. But if you have a conductor connected to the ground and put some charge nearby, that charge will attract or repel the other charges, so that you will be creating a charge distribution on the surface of this conductor. And the potential inside our volume will receive a contribution from the point charge that I put, that is this 1 over r minus r prime, plus there will be a contribution from the surface. And the charges on the surface. And the charges on the surface will contribute both this F and also this term over here. You see, if you make this conductor analogy, G is the potential. If you take the derivative of G with respect to the normal direction, you obtain the electric field in the normal direction. On one side of your conductor, you have an electric field given by dG over dN. On the other side of the conductor, you have a zero electric field. So dG over dN is nothing but the discontinuity in the electric field. But the discontinuity on the electric field across a surface gives us the surface charge density. So this dG over dN is basically the surface charge density created on the surface if you put a point charge inside.
As far as I remember, G is symmetric of R prime.
Not always, in fact. Depends on your surface. Your surface can be symmetric. In that case, it will be symmetric. If your surface is not symmetric, then it won't really be symmetric. You see, the differential equation satisfied by G is symmetric in R and R prime. So in fact, you can say that just looking at the differential equation, G should be a function of R minus R prime. And it actually is if there is no surface. But the surface kind of spoils it. Nevertheless, it should have this property though. It's Laplacian with respect to both r and r prime. It should be equal to minus 4 pi Dirac delta. You can have asymmetric terms, but their Laplacian should be 0.
How do we know this?
Hmm?
How do you know that the Laplacian is respect to both
Plus, I claim that g when r is on the boundary should be equal to g when r prime is on the boundary. They should be 0. What kind of this tells me that it should be symmetrical. Right? So you see, I have this function g, r and r prime. Okay, and let's say that this is equal to minus 4 pi Dirac delta cube r minus r prime. I know that g r prime r minus 4 pi Dirac delta cube r prime minus r. But this is minus 4 pi Dirac delta cube r minus r prime because Dirac delta is a symmetric function. So what do I know? Okay, so this doesn't really prove the first argument, but let's say this is equal to, so it proves that del r prime squared g of r prime minus g of r prime r, this should be equal to 0. No, sorry. Let me put a question mark over there. I'm not so sure if it is always satisfied. I know in the book it claims that the G should be always symmetrical.
The book says.
Yes, the book says it. I am not so sure. I have certain doubts. Let's say. Yes, other questions? Yes, Jihad. Questions? Some? Mm-hmm. The proof of which one? Which one?
Actually, can you prove this symmetry?
I cannot. I mean, that's why I put some questions over there. I will try to prove it on Wednesday or Friday, but not now. So if you tell me which step you don't agree, we can discuss that step. I mean, you see, whenever you are asking questions, okay, I don't understand this chapter, that just makes me think that you didn't read it. Or if you just ask me, okay, I don't understand this derivation, again, that makes me think that you just looked at it, you became pessimistic, and you just skipped it. Because if you start studying, you will realize which step you are stuck at. And if you realize which step you are stuck at, you can ask me that step. Or you can ask your friends that step. And then your friends can help you. Because going over a chapter, let's say, will take like 4 or 5 hours. And probably most of the part you could have already studied on your own. But if you just ask me or your friends just the point that you are stuck at, well, that in general takes like 5 minutes. And we don't have to repeat everything that you could have studied on your own. So, which step?
I want to agree. Furthermore, it satisfies the less boundary condition GB y comma x is equal to 0.
Can you repeat it?
Furthermore, it satisfies with less boundary condition GB y comma x is equal to 0 for
GD?
yx
YX?
y comma x in
Hmm.
parentheses.
The arguments, you mean?
Yeah.
Equal to 0?
For y is underscore boundary
Y on the boundary. Okay.
so it makes all g e x y of y is 0.
Well, I mean, you see, just this step doesn't say that. This step only says that if y is on the boundary, it is 0.
So what if x is on the boundary?
I don't know.
So
Hmm?
that's my question.
I don't know. I cannot prove it. I'm not so convinced. I should look at it in more detail, hopefully until our next lecture. So anybody who has an answer?
I just find a mathematical proof
Hmm?
I found a mathematical proof of its function symmetry, but not physical interpretation.
What is the value of this method? Do we apply it anywhere? Obviously, it has to be symmetric in some cases. How do we use that?
Well, let's see. One nice thing is that here I could easily ignore the arguments in this equation. That's kind of nice. Secondly, you see, another place where we can use is, how do we know that, okay, we derived it by assuming that phi satisfies our Poisson equation, but can we show that this integral, can we check our result that this satisfies the Poisson equation with the boundary conditions? You see, here G satisfies Laplacian of G is equal to minus 4 pi Dirac delta R minus R prime. So let's apply this Laplacian with respect to R on phi. This will be equal to the volume integral rho of R prime. Now the Laplacian with respect to R of G plus some terms, ds. Well, these are phi R prime. This is ds prime. We are taking the derivative with respect to the R prime coordinates. Phi R prime d by dn R squared of G minus d phi by dn prime R Laplacian with respect to R of G. Now we know that this is minus 4 pi, the three-dimensional Dirac delta R minus R prime. So if I evaluated the volume integral, I just obtained minus 4 pi rho of R. That's the Poisson equation that phi should satisfy. Now let's look at the other terms. Now this is, again, minus 4 pi Dirac delta of R minus R prime, but R prime is a point in my surface. R is a point inside my surface. R prime is a point on the surface. So there's no way that R is equal to R prime. So if R is never equal to R prime, this is equal to 0. Well, the same thing over here. If R is never equal to R prime, this is 0. So the phi does satisfy the Poisson equation if obtained by using those integrals. Now let's look at the boundary condition. We know the value of phi on the boundary. Let's say. When R is on the boundary, you see R is on the boundary, we know its value. We set G on the boundary to be 0. This is equal to dv prime rho of R prime G of R prime, or R prime R if it is symmetric, plus this term. Now the question is, how can we show that this is satisfied? You see, here we have the value of the potential on the boundary. Here we have the potential on the boundary. How can we tell that this equation is always satisfied? You see, G should be such that this equation is always satisfied, whatever phi on the boundary is. How can you see that? Well, we said that G on the boundary is 0. This term is 0 anyway. So in fact, we are left with a single term. Okay, this will be a second homework for you. For next week.
If we do set a restriction on G in order to find this, would
Well-
this argument with that thing?
These are the only things we know about G. There are no other restrictions.
We know that it must satisfy this equation because we derived it from the divergence.
Mhm.
So if we find that it satisfies only in a certain condition for G,
Mhm.
so this formulation is a proof for this restriction on G.
Okay. Yep. Yes, other questions? If you don't participate in the questions, I will just ask you to ask questions. Yes, Anil, now it's your turn. And then it will be Riza, who is also not speaking that much. Or if you want, you can also go ahead first, Riza, if you have questions. It looks so, but it's not. You see, we said that, okay, G is the potential corresponding to a point charge in our volume if we imagine that on the boundary there is a grounded conducting plane. Then dG by dN would be the discontinuity in the perpendicular direction of the electric field, but that discontinuity would basically correspond to some surface charge density. Of course, that is the surface charge density created by a point charge in our volume. If we put a point charge in our volume, it will create a surface charge density in the nearby conductor, but that surface charge density will not be located at a single point. Right? So that won't be a Dirac delta. Or maybe I did a mistake in the previous steps. G is 0 on the boundary. Plus some f, some function f. 1 over r minus r prime would not be 0 on an arbitrary boundary, so we have to add this function f to make sure that it is 0 on the boundary. Yeah, you don't know.
So we have some ambiguity here when we say that R or phi R belongs to the surface. And we say this because in order to find phi in the first place, to isolate phi, we have evaluated phi Dirac delta. So in the combination of this, we evaluate phi, the integral of phi Dirac delta over the volume. So if R is at the surface, do we include it in the volume or not?
Do you agree with him?
Because if we don't include it, then this is not satisfied. This shouldn't be satisfied.
Yeah, the potential should be continuous. So I'm inside my volume. I'm approaching this point on the volume. Everything is continuous. I get very, very close. Since I get very, very close, G is 0. Since it's 0 on the boundary, so it should also change continuously. So G is 0. And up to this point, the only thing I used was that G is equal to 0 on the boundary. So very, very close to the boundary, but inside my volume, I should have this equality. I'm very close. So of course there might be some very small corrections which will go to 0 eventually as that 0 vector goes to actually 0 vector. In fact, this kind of proves that this solution and phi is equal to minus 4 pi rho, and phi on the boundary is phi boundary, let's say. These system of equations and this integral expression are equivalent. They contain the same information. So this expression on its own should tell me what the boundary value is. And that is what I'm actually writing over here. I just approach a point on the boundary. So if as I get very, very close to that point on the boundary, this integral equation should be satisfied. Does it? How do I know that this integral equation is satisfied?
We should already know it from the proof of that expression.
Well, you see, I'm trying to go the other way around. Can we go the other way around? So what other information we need to use to be able to go the other way around?
We need to set some conditions on G.
So what are they? Or phi? Well, the trivial one would be the derivative of G with respect to n on the boundary should be kind of a Dirac delta function. That is what Jihad had suggested.
Or there should be a state function.
But, I mean, if it was a Dirac delta function, it would have been really great. Because then we have the Dirac delta, we can take the surface, a two-dimensional Dirac delta, we can take the surface integral, etc., and we are done. But, as you said, I mean, evaluated on the surface, it's not even a step function, it's the charge density, surface charge density created on the surface, which won't be a Dirac delta function. I don't expect it to be a Dirac delta function. But if it's not a Dirac delta function, then there is something else. Some other property of the solutions of Poisson's equation that we are missing. As you said, there is some condition, there should be some condition. But what is that condition? Plus, it is a condition on G or on phi. You see, we know that both G and phi, they satisfy the Poisson's equation. And solutions of the Poisson equation, they have some general properties, which we didn't use up to this point. What properties do they have that we have been missing in our derivation? So that's why I want to go the other way around, so that we can get a deeper understanding of the solutions. For example, we can try a simple example and see whether this works or not. Let's check it in a simple example. A sphere with a uniform surface charge density. Radius r, total charge q. This will be kind of too trivial, but let's see how it works. Well, the potential on the boundary will be just q over r. That is the potential on the boundary. Now, the Green's function, what's the Green's function? Well, we are looking at the inside. What's the Green's function? It will be 1 over, let's say, r minus r0 minus you see, the Green's function is you imagine a point charge over here at the position r0. If you put a charge q inside, then you get the corresponding image charge somewhere over here. Let's say it will be q prime, and we can evaluate what q prime is eventually. 1 over r minus r0 prime. As I said, we can evaluate them eventually. Now, dg by dn would be just dg by dr. Which will be, well, d by dr of 1 over square root of r squared plus r0 squared minus twice r0 cosine theta minus q prime 1 over square root of r squared plus r0 squared minus 2r r0 prime, no, these are r0 prime cosine theta. Okay. Now dg by, well, if you take the, okay, so it turned out to be not so trivial, at least not something to be finished in the remaining 1 minute. So you need to take the derivative with respect to r, put it over here. We already know what the value of this is. Well, let's do it in a different way. Q over phi of r, if the above equation is satisfied, we know that it is some number, ds prime, phi of r prime, dg by dr. I mean, let's test that whether this is satisfied. Well, phi on the boundary is q over r. This coefficient over here, well, this is on the boundary. On the boundary, it is a constant, so it is q over r, ds prime, dg by dr. But this integral, remember, this is a closed surface. This integral just gives me minus 4 pi, because the derivative g is the potential created by a point charge, so its radial derivative is the radial component of the electric field created by a point charge inside my volume. But if I integrate the electric field created by a unit point charge over a closed surface, Gauss's theorem tells me that it is just it's just 4 pi times the total charge inside. Well, the derivative is minus the electric field, so I have this minus sign. So basically, this tells me that this coefficient should be minus 1 over 4 pi. So, check. It works. Well, of course, you could have just evaluated the electric field explicitly, evaluated the surface integral. That's another thing we could have done, but it will take a long time. It works. That is, if the potential is constant. But it should also work if the potential is not a constant. So can we see it? How can we see it? Okay, there's still a big question mark over there. So that is kind of the end of for today. Okay, about the pre-reports, I mean, the pre-reports should be about the chapters that we are